The origins of CUDA were always to go beyond CUDA. That was the whole point of it.
All right, welcome to the Beyond CUDA podcast. I'm your host, Jeff Tatarchuk, co-founder of TensorWave, the AMD GPU cloud. Today's guest we have on our show is Greg Diamos. He has his PhD in electrical engineering from Georgia Tech. He was involved in the early days of CUDA, working on NVIDIA's Volta GPU, and a key force behind scaling deep learning at Baidu. He helped launch MLPerf, which is the industry standard benchmark for ML systems. He's worked across the board from leading AI startups to the big three chip giants, Nvidia, Intel, and AMD. And he's now focused on an exciting open source project called ScalarLM, which we'll dive into later in the show. But Greg, great to see you, man. Thanks for joining us.
Great to be here, Jeff. Thanks for having me.
Yeah, I'd like to, man, you have an amazing journey. As I was going through your history, I'd like to start from the very beginning. Where did your interest in electrical engineering come from?
Yeah, it actually is a strange story now that I go back and think about it. It started when I was 10. So when I was 10 years old, my dad really wanted to get out into nature. And so he decided to move us out into the desert of Arizona. Not the cities that you're probably familiar with, but try and pick a national park and get as close to that as possible. And so it was very peaceful, but there were no other children and there wasn't really anything to do. So I had 10 years to contemplate my thoughts in the desert. And luckily for me, my mom was a database administrator for IBM. And when they were throwing away the old mainframes, she would throw them in the back of the car and put them in our garage. And I was originally bored, but I had nothing else to do. And I just sat there for 10 years tinkering with them. Well, I got really fascinated of how could people build something that's that complicated that actually works. So I taught myself to program, and I thought, okay, I'm going to go off and go to school, and I'm going to learn how to build a computer just like this. And so I did all the classes, and I got like halfway through a PhD program, and I got really fortunate. So this was just a chance. I don't know even how this happened. I applied for a job at Nvidia because it seemed like we were building fast accelerators, and I got hired into the original CUDA team. So John Nichols was the compute architect who had the vision for CUDA. Previously built that as a startup, and it got incorporated into Nvidia, and Jensen said, "Let's take it to market."
Yeah, how did that come about? How did CUDA and NVIDIA join forces? What was CUDA before NVIDIA, and how did it get engrafted in?
There are a lot of people that over time came together to build CUDA. I think Mass Par was John's startup, and it had basically built a SIMD accelerator in the spirit of the old Cray vector processors in the 80s and the 90s, and they tried to take it to market. And it made reasonable progress for a startup. I think they had something like 200 customers in the 90s. But then as CPUs, superscalar CPUs, took over high performance computing in the 90s. And so then, that kind of, they didn't make it as far as they wanted to. But when I talked to John, like his perspective was, um, if you build a faster computer, people are always going to find something new and amazing to do with it, and it's going to change the world. And then he would tell me, it happened here, and it happened here, and it happened here. And he said, so that's what we're going to do. We're just going to focus on performance. And that's what we did in the early days. We had added features into the GPU that seemed, they seemed maybe hard to program. I think the joke at the time was that CUDA was really fast, but it was really difficult to program. One of the features that went in when I was there was shared memory, hardware support for shared memory. And I was writing some of these like assembly kernels that would try and take advantage of shared memory. And it was fast, but then the question was, what do you do with it? Like, what kinds of applications can you build on top of that? And we had to kind of start at the very low level of let's just write a kernel that loads data out of memory. And let's make sure that it can get good efficiency, or let's make sure that we can write a communication primitive, like we can exchange data between threads and it can be done efficiently. And so it was extremely low level back in, the early days. But then, layer by layer over many years, it took almost a decade. We kind of built out to, complete applications in many domains.
Wow, that's fascinating because I remember reading in the book that just came out, The NVIDIA Way, and seeing the story of Jensen believing in the vision of CUDA early on and taking the risk to develop this over time, not knowing that it would actually be the thing that would dominate the AI space and create what it is today. As CUDA has dominated the the AI research landscape for the last decade. In hindsight, what do you think CUDA got right in the early days that kind of got us to where we're at today?
Definitely. What did CUDA get right? It really got performance right. So it was at a time when everyone was saying, okay, sure, parallel computing, it's more scalable. There's the end of Dennard scaling. It's hard to keep making CPUs faster, but there's still room behind multi-core, behind parallelism, behind SIMD. John would call it massive parallelism. Um, there's still room to get performance out of that. It's just hard to program. And I think being willing to bet on it in spite of it being hard to program was important because let me just give an example. At one point, it really was hard to program. At one point, I tried porting a web browser to CUDA. Like imagine porting Chrome to CUDA,
Hmm.
and we got a fair amount of the way there. It did compile and it did run. And then I ran like a simple benchmark on it, and it was about 40 times slower. And it had taken me about 4 months to port. So it was a horrible nightmare to port a web browser to CUDA. But if you had the right application, some of the other things we were looking at were sorting, um, or we looked at database applications like relational joins. Um, if you got the right kernel and you had a really optimized implementation of it, you're willing to put in, I might have put in 4 months into one of those kernels, and the kernel might have been, 300 lines of code, but it took 4 months because it was so difficult to get every single detail scheduled exactly right. It was really fast. We could get pretty huge speed ups. So compared to, Intel server chips at the time, you could get a 20x speed up, or it was like you could maybe get over 50x in compute and 20x in memory. And so you could see the light at the end of the tunnel. You could see, okay, if only we can figure this programming thing out, there's something real here. We can build much, much faster computers.
And why would you say everybody says that CUDA is NVIDIA's moat? Why do they say that CUDA is NVIDIA's moat, and why is it so hard to replicate today and overcome? What is
So
it that
I'm,
makes it so special?
so I'm going to fast forward to when deep learning took off. This is when my personal experience with it is a lot of it is through MLPerf, where we define the set of applications that would be used in deep learning, and then the whole hardware industry pivoted to AI. So everyone, including Intel, AMD,
What year
Qualcomm,
was this?
it's gonna be around 2014 to 2016.
Hmm.
So around this time, the writing was on the wall, AI was working, and this was gonna be the workload of the future, and computers needed to run this workload. So everyone realized they needed to run this on their chip. So both people who had existing chips tried to port deep learning to their chips, and many new startups emerged. I think it was 40 plus that we knew about, of people who tried to build new accelerators to accelerate AI. And so I got to see up close and personal some of the reasons why it was difficult to do that. I think a lot of people got lulled in by the idea that, oh, deep learning is simple. The kind of core computational primitives are matrix multiplication. It was really a wonderful coincidence or accident or something that created that we could just accelerate matrix multiplication, and then you can run AI. And so when you're building a chip, you think, oh, but it's so easy to build that. Like building a CPU was so hard, or building a graphics engine was so hard, but building a matrix multiply accelerator, people have been doing that since the 1940s. That's the history of computing in the Manhattan Project. Like, we know how to do that.
Right.
Let's do that. And so everybody did. And the thing that they ran into was the software stack. They would build chips that had really great peak ops. They would build one like hand-designed data path that would run one convolutional layer, and they get good flops for that one layer. And then you'd start thinking about, okay, but now I need to put that in the hands of real users. I need to put that in the hands of machine learning engineers who are developing models. And then you start running into maybe it would actually be helpful to get good performance and have flexibility because programmers, the original community was very experiment driven. So the machine learning engineers would think, oh, but I have this idea or I want to run this experiment. And so they would care that the experiment would complete, but they would also care about how quickly they could prototype the next experiment, run the next experiment, and then learn from that and move on. And so the first generation of AI chips were pretty great on perf for maybe one model, but then real users would try something that they were working on and then it would just fall to pieces because it just wouldn't work. And then they'd have to get down into, am I copying, like some of the first ones were really, really rigid.
Right.
If it's not a matrix, it doesn't work. Or if it's
Mm.
not a matrix, I need to start writing command buffers for a DMA engine. And then machine learning engineers are like, I don't even know what those words mean. So that's the moat. The CUDA moat is it's so interesting in hindsight. Like I really think some of the founders like John and even Jensen like really had great vision for this. Because CUDA didn't just jump to deep learning. CUDA explored it ballpark of 30 to 40 different verticals that included cryptography, that included physics simulation, computational chemistry, the whole like sciences in high performance computing. And so it wasn't just the deep learning ran on CUDA, it was, really a wide range of applications. And that made it flexible.
Interesting. And yeah, Jensen, he was very determined, and he saw that there was something here, invested a lot of resources, and it seemed like the moat was very clear just in the last few years that that there's something that is insurmountable. But yet people are talking today about the moat is shrinking in some regard. What does that mean to you? What does that mean to you that the moat is shrinking, or is the moat actually shrinking? And is there a way to overcome that CUDA moat or crossover to the other side that truly expands compute and democratizes this? What are your thoughts on that?
Yeah, this is why I'm so interested in AMD in particular. It's actually a historical reason. AMD's GPU accelerators that they'd use for running machine learning workloads are built on the foundation of ATI, which was a GPU, right? It was basically at the same time that Nvidia was developing CUDA, the biggest market for GPUs at the time was graphics. It was accelerating real-time 3D games. And that market had been refined over 20 years. And there were really two companies left standing after 20 years. And one was Nvidia and one was ATI. And AMD ended up building their accelerators on the foundation of ATI, which has that hardware flexibility into it. It's if you zoom out like at a hardware level, the basic building blocks are very similar. Of you have memories and you have high performance memories and you have interconnect and you have this massive array of threads and then you do this like barrel scheduling for threads. And so the programming models of taking CUDA and then mapping it to like another accelerator versus mapping it onto AMD is substantially easier. It's not easier for the bulk of the work. The bulk of the work is of the perf is matrix multiplication. But then it's all of those little things that are extra that get you. And so all of those little things that are extra, they're much easier to program on something that's derived from a GPU than something that's built from scratch or that's something that takes a very different architecture approach. So I think that sets up AMD to have a huge leg up in climbing the CUDA mode. Now, in addition to that, there's a lot of software that's built on top of that. That's just how do you do math operations and how do you schedule threads and how do you like launch arrays of threads like that. GPU gets you those pieces, but you still have to build out to the application layer of how do I train this model? How do I distribute this model over like a large scale system with thousands of GPUs? So I think the thing I like the most about AMD is that they listen to feedback. Even early when we were at Baidu, they would come and say, oh, these are the labs who are building deep learning. What do you need to support? And it's a lot of work. I think AMD's had thousands of engineers working on that since 2018. And I don't want to diminish it, but it's like eventually you get it. Like eventually you fill in all of these pieces.
Yeah, and they have been. I've seen AMD has done a lot of work to hire engineers and put resources towards this. And it's interesting to me when I talk to various folks that have been involved at NVIDIA and AMD on the software architecture side of things, they all have varying opinions as to which direction they should go down that will actually crack this code and create a sustainable software stack. So what's your thought on it? What do you see as the opportunity on the AMD side when it comes to the software architecture that maybe AMD isn't paying attention to right now that they could spend a little bit more time focusing on to help close the gap on the software side?
Definitely. One thing I'd start with is I think more people should be using AMD. I think not at the very large scale yet, but at the small and medium scale. And the small and medium scale is pretty big, like the MI300, has 200 gigabytes of HBM. It has a huge capacity to run you could run 70 billion parameter LLMs on one GPU. So the small end is maybe not that small, but the small end is pretty stable. If you just wanted to spin up a container, spin up an inference service, download Hugging Face transformers, run it on an MI300, it'll probably just work and it'll get good performance. So that's something that you cannot say about most accelerators. And that was the thing a few years ago when I started poking into this that got me really excited about AMD, that they've made that much progress on the software stack. Even getting to that level is really hard. But you asked about what's the missing piece. I think AMD's made a lot of progress on scale out, so on running on larger scale than that, because of course, generative AI is so computationally intensive. These are the biggest models we've ever seen in the kind of history of machine learning. These are so computationally intensive. These transformers for things like GPT-4, Claude, Llama, these are just enormously computationally intensive algorithms. So you want to run them on a really large scale system. If you have a significant number of users, or if you want to train them, they need a really big system, not just one GPU. You need to start thinking about thousands or hundreds of thousands of GPUs. So getting scale out is maybe the next frontier for AMD. And they made a lot of progress over the last few years in inference. So you can look at the MLPerf results. Their inference servers on MI300 or 325 compared to H100 or H200 are effectively neck and neck on LLM inference. So they've made a lot of progress in being able to get that scale out for inference. Training is a little bit harder though. And I actually think it's a software ecosystem challenge. So I'm going to tell like a quick anecdote about this. So back in Baidu, we built out some of the first prototypes of distributed training. We actually built the first large-scale CUDA cluster in the world. It was around 1,000 GPUs, and it was the first one ever for deep learning. And so we prototyped a bunch of software on that. And one of the things we prototyped was distribution strategies and collectives, and then distributed training frameworks that didn't just use async, they used MPI. And the legacy of that is that some of the pieces of that, as a lot of that team actually went back and worked at Nvidia, got integrated into Megatron. So there's now this framework that's developed by Nvidia engineers, used to be Baidu engineers, of course, a bunch of new contributors too, but it's really a good way of doing distributed training. And it's one of the only good open source frameworks for distributed training that works at that scale. And the problem with it is that it's actually wonderful that it's open source, but because it's NVIDIA developed open source, it's not like PyTorch. It's not owned by a neutral third party. It's owned by, NVIDIA, who has even if there's some altruistic nature of making things open source, there's not really a strong motivation to fix bugs or to performance or tune performance for AMD or anyone else. So that's, I think, a big gap in the ecosystem, is that inference is probably completely fine. We have great open source frameworks like SGLang or VLLM in inference that are just fine and they're vendor neutral, but there really isn't like a vendor neutral, good, scaled out training framework.
This is a great transition for us to talk about what you're working on with ScalarLM. Maybe you can go into kind of your thought process behind Scalar. What is ScalarLM, and what are some of the things that ScalarLM contribute to helping solve some of these problems?
Yeah, so that's really what we're trying to do, is we're trying to just create a Megatron inspired, because they got a lot of the right software design issues. They got a good architecture, but just make it open source and neutral and third party that isn't tied into the NVIDIA ecosystem, so that it can run more efficiently on AMD. That's the motivation. We kept going into these. As in working with startups, I'd go in and look at what people are using. I'd go in and say, oh, there's this research lab that's training this model. They're trying to develop maybe a model that's better at reasoning, or they're trying to develop a model that's better at image generation. And so I'd go in and look at what they're doing. Or sometimes also there are these national interests, like maybe, but wait, GPT is great in English, but we don't speak English. We want to make sure that our region of the world has access to AI. And so we need to build our own foundation models in our own language and our own culture. And we have large like either just national interest in building models from scratch. So you go and look at these people training models. And the way the story would frequently go, we got maybe 10 of these of, okay, I started training on one of these existing training frameworks. If they come out of the Nvidia ecosystem, which is the majority, they'd say I'm training on Megatron, and they'd have some Megatron training system. Sometimes they come out of the Google ecosystem, and they'd say, oh, I'm training on TPUs. I'm training on jacks and TPUs. But the majority of it was in Megatron. And then they'd say, okay, now I want to try running this on, for example, like AMD accelerators. And what are the challenges? And the story would usually go of, okay, we have smart people. Let's take a team of 10 PhDs and let's port it. And then they do, and then they port it. And then they're able to take some training steps and they're able to measure performance. And then they look at that and they say, but I just spent 4 months or 6 months with my high-end team of PhDs who should be focusing on training model. And look, Megatron advanced by 300 PRs, and now I have to do an integration. If I keep doing this, I'm going to burn this entire team of just maintaining this in-house software stack that no one else is going to use. Or I could just use Megatron and just run on an Nvidia cluster. And so it really does lock them in. Like, it really prevents them from porting it because there's nothing in the ecosystem. And that's the motivation that we had for ScalarLM. That once we've seen enough of these things, we said, okay, we'll sign up, we'll do it. It's a lot of work, but we'll do it. Somebody has to do it if we're going to have this ecosystem.
Exactly. And tell us about some of the work that you are doing for ScalarLM, and maybe share a little bit about the roadmap on where you see things going in the next few months to quarters. And I know it's an open source project. And also share more about how others can get involved.
Sure. Yeah. We're in a V0.5, so this is the first release ever. And we really want feedback. So we want people to try it out. You can try it out. You can download it if you have access to AMD GPUs. We have pre-built images. You can build the images yourself. You can run them on single GPUs. You can run them on 8 GPUs. You can also scale out and start to run it on multiple nodes. And I think, Jeff, you asked about the roadmap. That's really where our head is at for the roadmap. We're trying to take this out to scale. We're trying to take this to the point where I should just be able to go and download this and then deploy it on my cluster. And then I can launch a training job very simply with a few lines of code, a simple script that just runs. I want to train Llama 4 and I have 1,000 GPUs. I should just be able to write a 50-line script and just press run, and it should immediately spin up the entire cluster and get good performance. And so scale is really, it's in the name. Scalar.
I like
Scale
it.
is on our roadmap.
I like it. And you are built on VLLM as well, right? VLLM, like you have a unified inference stack or inference and training stack. Talk about why you feel like that's important. I feel like one of the conversations we had, you mentioned that it's a bit controversial to include unified inference and training in the same stack. Talk about why that would be controversial and why you've decided to integrate that into the framework.
Yeah, I keep telling this to some of my friends in Meta, and then they're saying like that's not the right thing to do. You shouldn't do that.
Why are they saying that?
And then I asked them to think about it. Come on, tell me why. I know it's not how
Exactly.
you do it, but tell me why.
Yeah. And what's their
And
answer?
the reflection, one of my friends was reflecting on this, and he came back and he said, yeah, it's just because of how the teams are organized. There's a training team and an inference team. And so it's Conway's law. And then I'm thinking like, of course it is. That's what I've seen too. And it's so interesting because I feel like I had a little bit of a hand in this. Back in the early days of MLPerf, we're trying to come up with workloads, and so we're trying to say, oh, how should we partition the workloads? Like, how do we organize the space so that it makes sense? And we started with training, and then I was actually the first inference working group chair. So I created the MLPerf inference as something that was separate from the training benchmark. And I did it for Conway's Law because I looked in Baidu and I said, okay, what are people working on? And there was one team that was working on training, and there was a different team. There were big teams, like 50 people, 100 people teams, that was working on inference. And so I said, okay, go talk to each team and see what they're working on. And then different teams can contribute different benchmarks. We compared notes across Google and Microsoft and like big hyperscalers, leading AI labs. And man, it was I think it was a consequence of that we have set training and inference being separate. It's a consequence of deep learning came out of these really big hyperscalers first. And then these hyperscalers were so big that they had so many resources that it was completely fine to dedicate a 100-person team to do training and a 100-person team to do inference. That's not problematic at all. That's completely fine. We have thousands of people. But then the problem with that is then when you try and take it to the rest of the world, or you try and step back from first principles and say, what actually makes sense? What does it make sense for people building applications? Machine learning fundamentally requires learning. That's the point.
It's in the name.
And it shows up, right? If your model can never learn, we would be stuck at GPT-2 and it would never get better. And so would anyone's model who's doing any kind of work in AI at all today. So training is a fundamental piece, but training is not enough because someone has to use the model. And even the team developing the model has to use the model. You have to be able to eval the model or test out the model or red team the model and see if it's working correctly. So this whole idea of like training is one thing and then inference is another thing just doesn't really exist. It's a Conway's law artifact of the history of deep learning and AI. And I see this all over the place when you go and look at companies that don't have thousands of engineers. And I suspect even for companies that do have thousands of engineers, it's yes, you can burn resources, but why do you want to burn resources? It seems extremely inefficient. So that's the path that leads us down to unifying both. Like we just think it's a better architecture, it's more efficient. There's no reason at this point why they have to be separate other than historical reasons. I think we should just let go of the history and just live in the future.
Interesting. So you feel somewhat responsible for the initial segmentation of inference and training, and now you're working towards unifying them and bringing them back together again. I remember, I think what did you call it? Super alignment. Your super
Yeah.
alignment workflow and implementing that through Scalar. Now, what are some of the obstacles that you see in bringing these two things together?
It's a lot of software. We're at the very top of the CUDA moat, all the way up at the top. And there's so much stuff underneath that it's almost unmanageable. Like I think I was talking with one of our software architects and about this, and we're looking at a bug, like we're looking at a performance bug. And we're thinking like, okay, how do we even understand what's going on when we're training this large model that's distributed at all? And then we're sitting on Hugging Face and PyTorch, and then we're sitting on like the math libraries, and then we're sitting on the runtimes, and then like CUDA, and it's just there's an enormous amount of stuff going on there, and we're trying to take these two different really tall towers of software and then put them together. And so I think we've had to go back through and revisit every single layer one by one and say they just were not designed to be compatible because we had this inference and training separation. So yeah, it's been a fair amount of just stitching it back together. But I sometimes hear this concern of, but wait, but we didn't, isn't it optimized? Aren't there like inference optimizations that make sense? And aren't they different than like training optimizations that make sense? And I think that's probably true that there are optimizations within the software stack, certainly. And then even sometimes people say, oh, but we have inference chips or training chips that are optimized differently. I don't think it's the reality of how people are buying clusters today. If you're buying a 10,000 GPU cluster and then you say, but it can only run one thing, people look at that and say, really? Why am I paying so much money if it can do one thing?
Exactly.
Yeah.
Yeah,
So I think it's an intellectual argument, not like a practical argument.
that makes sense. So there's clearly a lot of problems that do need to be solved on the entire stack. And you and your team at ScalarLM are working to help solve some of those problems. Outside of the things that you are working on, what are some of the things that you think that as people are looking to build and grow beyond CUDA that you think would be some good areas for others to focus on building and solving some of these problems?
Sure. Yeah. So opportunities maybe to contribute. I'll probably say something to all my ML perf friends. I think we should have a unified training and inference benchmark. I think
There we
that would.
go. There we go. I like it. I like it.
I think I went to the last community meeting and people were starting to talk about reasoning, like the implications of reasoning. Clearly, it's coming. I think that was something that was on everyone's mind. And then what can we do about that? And how is that going to change the workloads? So I think looking into reasoning would be helpful, both at the application level, like if you're building models, but also looking at the software stack, like what in the software stack has to change in order to support reasoning. And I think that's from maybe the key areas we can think of are modeling. We can think like the scheduling in the inference and training frameworks, like distribution scheduling, distribution strategies, and then also kernels. I think one thing that's kind of coming together with this is, in addition to reasoning, is MOEs. So I think that we're seeing a shift in the models away from these giant, dense transformer layers to MOEs that are more efficient and having kernels that support that. The other area I think there could be great help with kernels is in different formats. So of course, we're on this roadmap of continuing to reduce precision because we're figuring out how to train models in lower precision. But that creates more kernel development work because the way that I write an int4 kernel or an FPA kernel is different than the way that I write a bfloat16 kernel or a float32 kernel. So the kernel development in particular, I think, is an area that could really use more contributions.
Yeah, that makes sense. Well, as somebody who you were there at the very beginnings of the CUDA journey, working with John Nichols, to seeing where things are at today, it's fascinating to hear your story going from all of those different pieces to being where you're at today. And when you think of beyond CUDA and going beyond CUDA, why do you think that's important for us to even be considering this? Why can't we just be dependent upon what's there and what's been created today?
I'm going to go back to the origins of CUDA for that. The origins of CUDA were always to go beyond CUDA. That was the whole point of it, that if we eventually build a faster computer and then it enables something new, it enabled generative AI, it enabled models that pass a Turing test. We're not done. There's no limit on how fast we can make computers, or we know what the limits are, and we're 20 orders of magnitude off of them. So in order to build something that's even faster and even more powerful, we need to go beyond CUDA. And I think the founders would agree with that.
Man, I couldn't have said it any better myself. And I think on that note, we can wrap things up. But Greg, thank you so much for taking the time and sharing your journey. And we're excited about continuing to work with you. Now, if people want to get involved in ScalarLM, where can they find you and the project? And yeah, how
We're
can they
on,
get involved?
yeah, thanks. We're on GitHub. So GitHub is a good place. Check out the code, file issues. We have a Discord channel. So there's links off of the code. You can talk to us directly. We're always hanging around the Bay Area. So we love to meet developers and people passionate about this. We also organize MLPerf. So we have the MLPerf community meetings. And if you want to just come by and say hi in person or meet some of the other people interested in high performance computing, I think that's a great place. We have cake too. So
There we go. I love it.
computers stay for the cake.
Exactly.